have a reputation for going around the world and telling people things they already know, and then reminding them of the implications of what they have to do next, and then having them ignore me. So you are part of a glorious tradition so far. But this could be the one that makes a big difference, rather than source address verification, which clearly did not. So I'm here to bridge a gap between a libc call and some signals. And there was an abstract, so you may already know some of what I'm planning to say. But let's rip something from the headlines, shall we? This week, the breach of the week is this one, Equifax, which is one of the 3 largest credit reporting bureaus, had somebody in their systems for some period of months copying sensitive stuff like social security numbers and whatnot. It turns out that as with Watergate, the problem is not the crime, it's the cover-up. It's now turning out that executives sold shares and things like that. But really, when I saw this come out, I didn't know what the details were going to be. I certainly didn't know it was going to be a finger-pointing contest involving Apache struts. But there is something I did know. When I saw the first headline before I read the first paragraph of news, I knew what you knew. What we all knew was, this is going to involve software and networks. Software is incredibly powerful because instead of having to build a machine out of levers and pulleys and gears and things that is very hard to change once you have committed to what it's supposed to do, software lets you build a machine of unlimited complexity and then change it every day. And networks are also extremely powerful because they allow pretty much anybody who has a pattern of ones and zeros to put that pattern of ones and zeros up next to other people's software, that logic, without actually visiting. So it's like you could try every possible key and every possible lock from your parents' basement. So if you combine these 2 very powerful things, networks and software, you get an incredibly dangerous mix. It is as though somebody could send a Federal Express package to your house and get your house to reconfigure its hallways while you were at work, which we would be panicked about, but this is worse, and for whatever reason, it's now considered normal. In any case, I'm sure struts is written in Java, because that's what that community likes to do, and so I'm sure that this community has no code that was implicated in this. And so let me dial back a couple of decades to something that this community did have a big hand in, and that was the Morris worm. I was at my desk in November of 1988. I worked at Digital Equipment Corporation. You may remember them. They made VAXes. And the starting conditions, as I've shown, was that pretty much all of the computers then connected to the NSFnet or the ARPANET that ran any kind of Unix were running a BSD derivative. In other words, there weren't a lot of System 5 derived systems plugged into that network. When I say BSD derivative, I mean maybe it really was BSD, maybe it was Ultrix, maybe it was Sonos, but the chances of having something that answers the TCP SYN packet speak BSD were extremely good this day. And at that time, for whatever reason, everything had inetd. There wasn't really a separate inetd package. There were no packages. And inetd was enabled by default. etcrc would just start it. And the config file didn't have any comments in it. Every single line in that file was live. Firewalls had not been invented yet. And so that meant that there was a data path from anybody on the internet to a piece of software called FingerD. And FingerD was a little bit like Whois daemon. It would receive one line of input from the network, and then it would take a look at that line of input and probably treat it as a username, and then give you stuff like the last login time of that user. Now, why you would want to leak that information to that network is beyond me even now, but we did that. We were very open, right? This is pre-commercialization, pre-privatization. The internet didn't have untrusted people on it. There were not Ukrainian teenagers trying to steal our credit cards because there were no e-commerce websites and there were no web browsers. It was a very safe network. And that's actually a problem because it is as though the internet was a boy in a bubble and we let it incubate in the bubble for its first 2 or 3 decades and then took the bubble away and said, germs. So the new element that day, and the reason this has its own Wikipedia page, is a guy named Robert T. Morris, Jr., who thought, you know, it would be really cool if we could make a self-propagating piece of software, right? The John, I think Varley, shockwave writer, had shown us sort of how this could be done, and he operationalized it. And of course, like most responsible programmers, which he was trying to be, he hobbled it. He tried to fix it so that it could not escape its network of origin, so that he could just test it locally. There was a bug in the hobbling code, and so it went everywhere. And for a first attempt, I have to say, I mean, it had some bugs, and Gene Spafford and others wrote papers about it. But for a first attempt, like the very first time he ever tried to run the a.out binary in that directory is when it worked. So he was a better programmer than he knew in some ways and a worse one in others. Anyway, so everybody got hit. Everybody has their stories. I remember talking to Rick Adams, who was the founder of UUNet, and I asked him, you know, gee, you had a sequent, so it's not clear to me how the Stack Overflow would have been able to put code in there that you could execute and so forth. And he said, well, there was a data path, but it didn't matter because all these years, this is Rick speaking, all these years I have never used a .rlogin file, so I have never allowed myself to go from one computer to another without having to type a password. I've just been typing my password all those times. Rlogin is like SSH, but without security. And then, of course, that was also enabled everywhere. And that was the propagation vector. So there was one external machine that got infected at UUNet, and then the rest were safe because there were no, just wasn't an authentication path. I, on the other hand, had rlogin files, and so we got hit pretty hard. One of the side effects, not mentioned in the Wikipedia page, is that this thing used a DNS lookup for the hinfo RR type, that is the host information. And that, because you didn't know if this was going to be a 68,000, in other words, a sun, or a VAX. So you knew if it was answering on fingerD, it had to be one of the two. And rather than guess, it would do an hinfo lookup because that would tell you if this was a sun or if this was a VAX. It was not a particularly popular record, and so it had to guess, and I think it just tried each one in some order if it couldn't find the hinfo. But as far as I know, this was the last time that hinfo was ever used. Certainly my symbolics used it, but that was before. Anyway, so this, because it involved BSD, is our problem. This was us. Those of you in this room who were online that day would remember that the CMU cert was created as an outcome of one of many outcomes of this. This was the first time that computers were used in this interesting way, and BSD was at the heart of all of it. So the thing about C is that it's just so darn pretty. You know, that code looks like what it does. And you know, there's a lot of languages that would have an awful lot more hair in it than this. But I'm sure that those of you who didn't already know this understand that the flaw in this design is that we're writing into this pointer that we received as an argument, and we're incrementing that pointer and then writing more stuff into the locations after that pointer. And we're doing that until we hit the end of a line or the end of the file. There is no knowledge in this function of how big the buffer is that is being written into by this function. And that is how the Morris worm got in. The source code to fingerD was widely known, so you knew how big the buffer was. and you knew what the stack frame above it was going to look like, and so it was very easy to just write the necessary amount of garbage to get beyond that buffer and into the frame pointer and the stack pointer and so forth. And so you would put VAX machine code or Sun machine code into the stack, which was then executable. I don't know why. And then you would change the return pointer on the stack to point at the code you had just uploaded, and presto, it gives you a shell because that's the code that you put up there. Now, this happens every day now, so you guys are looking at this and saying, well, sure, why wouldn't you do it that way? But this was the first time we had ever seen this done. And certainly it was the first time it was done at scale. Anyway, so, here's a test. I wrote a program that put a 5-character buffer right before another 5-character buffer, and then I ran it and gave it 10 characters, and as you can see, the overflow variable, the thing that followed the buffer on the stack frame, ended up with the last 5 characters of what I gave it. So I tested this. Now, you'll note I was using FreeBSD. And so FreeBSD knows at some level that getS is unsafe. And so when you try to link the program, it says, no, 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 you should not be doing this. But I gotta say, when I am installing something from ports and it's streaming awful lot of stuff, this is a message I might not notice. And nowadays I use packages, so I'm not even running the compiler or the linker, so somebody saw that message. And then it gives you, this is the only libc change I know of that pollutes your standard error stream with a warning message when you call a certain function. That's just really rare because that error stream might be getting parsed by somebody else, and so you might be breaking a program that was depending on silence here. But it was deemed important enough that we really had to get these warnings out where people could see them. And what I like about that is that it's something. What I don't like is we had to do something, and this is something, so we did it. I thought, since Linux won the war, right, it's got much bigger rooms than this, full of Linux aficionados today listening to people talk. I thought, since they're commercially accepted, they've got, IBM uses them and so forth, they must have come up with a better solution. No. In Linux, there are no warnings. The code is still there, it all just works. But you at least have a man page that if you read it, and if you understand what it's telling you, and if you're able to somehow get over the belief gap of, if it's that dangerous, why is it here? It must not be as dangerous as they say, or they would have removed it. Then yes, you would be the one programmer out of 10,000 who actually sees this and says, in that case, I'm not going to use this function. The other 9,000 and some are not going to see this at all, or they're not going to believe it, or whatever. And I do want to say that that's 1 out of 10,000 programmers that read the man page of something they intend to call. It's a much smaller number, a smaller fraction of the population who will read the man page on every function that is called by code that they are newly maintaining. In other words, most people don't audit source code using man pages to find out if the previous author shouldn't have called this function. What I'm trying to describe is a situation that affected 100% of the internet 30 years ago and is still with us today, has effectively not been mitigated. Early Hewlett-Packard printers had a TCP/IP stack in them, or they had a separate box that would connect to the Centronics port and then offer network services. And it was very cool. It was very nice to be able to access that printer from anywhere on the network, because previously you would have had to get an Apple printer and speak Apple talk to get that behavior. So Will thought that was great. But there is a version of code out there that will attack that printer, overflow its buffer, which is using getS, and fill that printer's stack with a whole return-oriented operating system. And we'll give it the ability to relay spam and DDoS people for you and so on. And so to the extent that any of those printers still exist and are reachable outside firewalls, they are probably part of more than one botnet. And indeed, getS is a parser. I know it's a degenerative form of a parser. It's, all it does is it looks for the new line as framing, but that is a form of parsing. And as long as people write parsers and connect them to the internet, you're going to be listening to people like me give talks like this one. It's much better to use a parser somebody else wrote, not because they get the blame, but because it may already have been audited. So I want to say that getS is the tip of an iceberg, and there's a bunch of other pretty ugly stuff down in there. strcpy and sprintf and strcat don't know the size of their output buffers either. Now, that doesn't mean that they are automatically unsafe, because you can audit them. You can look at the source code, figure out where sprintf is being called, look at the size of the buffer that it's writing into, look at the format string, and actually do hand verification to determine whether an overflow is possible. I wish that we could automate that, and GCC certainly tries. I know it's parsing those format strings now, but that's often just won't work. You often don't know the size of the buffer, or you don't know the size of the ingredients that are going to get passed in as arguments and expanded from the format string and so forth. So there's no way to machine automate the verification that can be done, but at least theoretically it is possible to verify these function calls. So evidently somebody, I don't know where or when, determined that this business of not knowing the size of your buffer was a problem, and that's where strncpy, snprintf, strncat came from. And that was a little bit better, because it won't write beyond the buffer that you said. On the other hand, it also won't always add a terminating null character. And so if you don't check the return value of some of these functions, you will end up with a unterminated string, which if you then try and use it, you'll be walking through all kinds of other memory looking for a null that belonged to somebody else. In other words, strncpy and so forth showed, it's actually the worst of all possible worlds. It showed awareness that there's a problem, and then it solved it in a really incomprehensibly bad way. So eventually we got strlcpy and strlcat. And I learned about these because I got patches to bind version 4. Somebody said, I did a format string audit on your code, and there were problems, and so it was a patch that changed every sprintf into an snprintf of the appropriate buffer size, and it changed every strcpy or whatever to one of these strlcopies and so forth. And the people who sent me this patch were well respected at the time. They were not idiots, they were not newbies, but they were wrong. And as happens to anybody who grew up on Usenet, when somebody is wrong, I engage with them. And so I had this conversation about truncation effects, which is that if you change it so that the buffer overflow doesn't occur, and you're guaranteeing that a null is going to be there so you're not walking off the end of the string, you might end up creating values as a result of these function calls that the surrounding code is not prepared to deal with. In other words, you haven't removed the risk of the program entering an undefined state. All you've done is remove a particular risk from a particular type of buffer overflow or string wildness. And so really, what you need to do is change every one of these things so that you're checking the return value and doing something, like returning failure to the caller of the function that you're modifying, or do something. Just do something. Don't let it create a truncated value that then gets syslogged in some other way and breaks something else down the line. That's craziness. They did not agree. I did not take the patches. And as far as I know, they still think I'm crazy, but they may be right. Anyway, what I want to remind everybody is that there was a version of SSH that didn't even have a version number because it was just SSH. We now call it SSH version 1 in order to differentiate it from SSH version 2. But the very first CVE ever published on SSH was an integer underflow. There was a 16-bit value that was signed when it should have been unsigned or something like that, and some math happened, and it ended up with going to a high number instead of a negative number, and that high number caused the surrounding code to then bypass various other checks, and so because of an integer underflow that did not involve any buffer or any strings or any heap smash or stack smash, just an integer underflow allowed a root shell to be created in that environment. So if you solve for undefined program state in a containerized way that doesn't sort of glue into the context in which that state is being created, you may be creating problems worse than the one you started with that will be then harder to debug and harder to detect. So I think that strl copy and strl cat probably should have had, and if it overflows, we're going to abort. And then a separate version called strl copy underbar unsafe would expect you to check the return code and do the right thing if truncation had occurred. Clearly, I did not win that war. Now, since there's badness, we should figure out where it came from. Not exactly whose fault it is, but how we could keep more badness of the same kind from hitting us again. I believe that complexity is the real enemy of security. And I realize that usability is also at odds with security, but complexity is where vulnerability comes from. We are creating digital infrastructure, we and others like us, that is so complicated that only the attacker could possibly understand it. And we should be looking in the mirror every day and saying that before we go to work, because that might lead us toward more simplicity as a design primitive. C is too simple. This lack of bounds checking, yes, I suppose it made it faster than the associated Pascal program of the early era, but it's not making very much performance difference now. So this business that you pass an array into some function and it receives it as a pointer and it doesn't know how big the array was, may have had some kind of performance benefit when we had a 64K address space and we're using bank switching to move the kernel out of the way. But it does not make sense today, and yet here we are. So libc it kind of came with C itself. I realize that we've got standards communities around C and libc and the rest of the Unix environment now. But early on, it was just, well, we've got a language, we need a library, and so they wrote a library in the language they had and started using the library to write the programs that they needed. But the people who were doing this had just published a book called Software Tools in Pascal, and had previously published a book called Software Tools. And if you look at early libc, including this, and you look at it in light of those two books, you're going to find out that they had been thinking along these lines for 10 years before GetS was created. But Software Tools created a language called RAT4, Rational Fortran. It looked a little bit like C. But the underlying Fortran that it was getting translated into had bounds checking. So you could do something like GetS in RAT4 and it would be safe. So they weren't thinking in terms of safety because they thought, well, at the moment, we are the programmers who are using this language and we know better than to do the wrong thing, which, as far as I know, was true. As is true in a lot of my own work, if I'd known it was going to be so popular, I would have been more careful about it. So when ANSI came out, they had the goal, because they had system vendors and compiler vendors as the members of the committee in question. They did not want to invalidate existing source code. They didn't want it to be that, I'm sorry, ANSI is a completely different language. You're going to get a lot of compiler errors and you're going to have to modify all your code. Yes, we got compiler errors and warnings and so forth, because there were some things about C that were so horrible that there wasn't a way to standardize them. But in general, ANSI didn't break anything they didn't absolutely have to break. So after the POSIX thing came out, POSIX, by the way, was a superset of ANSI. It was like, yes, this is the stuff that would be true for all C compilers, for example, on Mac of that era, or even a MS-DOS machine of that era. And then separately, here's a bunch of other library calls on top of that that would only work on a system that had path names, like create and things like that. So they were certainly not, the POSIX people were not going to say getS is out of here. They had to be a proper superset of ANSI. And I talked to Kirk McCusick about this because he was on the POSIX committee in question. And he said, yes, we had just lived through the Morris worm. We argued strenuously that getS not be part of the POSIX standard, but no one was willing to remove something that was in ANSI, and the ANSI people were not returning our calls. So what we have here is market forces. Anybody who gets into an argument with a libertarian who tells you how smart the invisible hand of the market is, you should tell them this story. So in a language called IFEL, a concept was developed called design by contract or programming by contract. You'll see hints of this in the Bind 9 source code because the chief architect of Bind 9, sort of before it was shipped, was a guy named Bob Halley, and he had just done a whole lot of work in IFEL. And so he developed a set of .h files that were included in the, in Bind 9 that, as far as I know, are still there, because there are 4 different kinds of assertions. Yes, they all lead to dumping core and printing a message, but it's the assertion of what state I inherited from my caller versus which one my caller created before they returned to me and so forth. So yes, they all devolved down to a call to assert, but from 4 different directions. And it was really interesting, connoisseur's version of assertion checking. And it really helped me, even though I didn't love Bob's design. I have no code in Bind 9, so it just didn't hurt me. But it was very interesting to me to see that you could raise this to such an art form. And I had long believed that program state was either defined or undefined at any given moment, and you either knew it or didn't know it, and you either could know it or could not know it, and that this was a way of tightening things up a bit. So I'm proud to say that although Bind 4, during my years with it, and Bind 8, which was all of its years, had a whole bunch of stack smash, heap smash, all kinds of bugs. There was a lot of ways to get root shells out of that stuff. Bind 9 has had a number of CVEs. There have been a lot of packets of death over the years that have caused Bind 9 to trigger an assertion and die. But that's it. There are no root shell compromises. There's never been a way to get Bind to execute code that the operator wouldn't have approved of. And that's because of this approach. So yeah, that means Bind 9 has a bad reputation for croaking and falling over, but what it really means is that it will never continue after an undefined state has been reached or could have been reached. I like that. I don't mind putting a nanny script around my name server to restart it if it dies. I do mind not knowing that it's willing to make a root shell for anybody who asks it. So a function caller, in my opinion, should be able to have a reasonable expectation of the function's results and side effects. But in the case of getS, that expectation is not reasonable. And the reason you can't audit this is that getS is not, it doesn't matter what size buffer you give it, you don't know what the input stream is going to contain. And so at the time that you're looking at the program, all you know is that after I call getS, my program state is no longer defined. So I've shown here an assert that I've actually used fairly often, which is to say, yeah, I've audited the heck out of my format string. I don't believe that assertion is going to get triggered, but I'm going to express that belief as an assertion. I'm going to have it be that anybody who's looking at this code knows that the statement after this one cannot have been reached if there was a buffer overflow here, because that'll help a lot. So this is using assertions more as documentation. And yeah, that's sometimes you get bit, and it turns out that it's a fairly common case, and you didn't do your audit carefully enough. That's pretty much where most of the bind assertions have come from. Now, I'd like to be able to describe for you, wave my arms about some pragmas that you could give a compiler, sort of like the old lint primitives, to tell it what you're doing here and what the human knows, what the programmer knows, in order to guide some kind of machine verification or even machine-oriented warning generation. But I can't think of it. I just don't know, especially in the case where SNPrintf's target is a pointer that was passed into it. I don't know how to express verification data. So at the moment, we're limited to comments, which is, I checked this for buffer overrun. Paul Vixie, September 2017, as a comment, would maybe tell somebody, Paul's often wrong, I better look at it myself, or, okay, it's been checked that recently. But we all know that what will happen is that the surrounding code will be modified, invalidating the audit I did. The comment won't be removed, and then we're back where we started. So I really don't know what is the solution to design by contract around this kind of stuff. But I do want to say again, getS can't be verified. You just don't know what's going to be in the input stream. And so it makes no difference what the buffer, what the size of the buffer was. Once you call it, you're in undefined territory. Maybe you've been hacked, maybe you haven't. But because you don't know you haven't, you have to assume that you have. So I find that it is hard to be BSD specific in my work today. Certainly, my company is full of Debian people because that's who you can hire on the open market. So I don't have any code in any of our products, and I don't know the root password to anything and so forth, and everybody there likes that. At home, I'm still running FreeBSD because I love ZFS, and I love Beehive, and I really appreciate Clang and LLVM, and it's the environment I'm familiar with. And so it's rare, though, that when I think about developing a product or developing software or a new protocol or whatever, that I'm going to be BSD specific. I just am not going to limit my market size to just this room or people like us who think this is a cool system. I'm going to make sure it's as portable as possible. Here, today, I'm talking about BSD problems. I mentioned that the Morris worm was our problem, and we have not solved it. And I'm about to make a BSD-specific recommendation. So I'm glad to have something that I can talk about that is not portable and doesn't also have to be done on Linux. And that is a change that I want all the BSDs to make. So we're lucky in a sense that there aren't commercial derivatives like Sonos and Ultrix anymore, because they would have product management teams who would look at this and say, you're crazy, we can't do this. Your stuff's free. You can do this, you can get away with this. And if it means that somebody somewhere downloads a package that is calling getS and that package doesn't work, or you change the shared library and so it's a package they already had that was using getS and all of a sudden it's dumping core, you can get away with that. You will not lose money because you're not making money now. And I believe that if BSD did this, it would be bragging rights. Look how bold we are. It would be being able to look the Linux GNU libc people in the eye and say, you people are afraid. So I mentioned some signals and a bridge from a library call to those signals. SIGPIPE is what happens if you write to an orphaned pipe. You just get this signal, and you could catch the signal. I'll certainly tell you that in cron, we had to catch that signal because bad things can happen. But for the most part, people that are writing to a file descriptor don't even know that it could be a pipe, so they're not going to catch the SIGPIPE signal. And this is very good because otherwise, if you had a shell pipeline, A pipe to B, pipe to C, and B died, yeah, C is going to get an EOF on its input and probably die also, but A would just continue running because nobody's looking at the output or at the return value of the write call that is going into what might be a pipe. And I think that's why we have SIGPIPE. I think that the people who developed the first shell, this was before the Bourne shell, were having pipelines collapse, and they didn't have a good way to make sure that they swept up all the debris, because some of this stuff was just running in an infinite loop, continuing to write to a pipe that was returning -1 every time they did it. And so they thought, well, we could audit all of our code and make sure that we always look at the right value and exit if we get a write failure, or we could add SIGPIPE and then we wouldn't have to audit anything. That is similar to what I'm recommending for GetS. SIGILL is it's illegal instruction. That means that your program counter, your PC register, probably points into the middle of some ASCII text somewhere because you did something crazy. And again, you can catch this, but unless you're a debugger or an interpreter, you wouldn't know what to do. I mean, how do you recover from that? How did my program counter get there, and where was it before? This is not something you can fix with set jump and long jump. And this is the right approach. If you get to a situation where you no longer have any confidence that your program state is defined or could be defined or theoretically known, you should not keep executing. You should stop right then and there. That should be your last millisecond on Earth. So let me explain that BSD's sins go deeper. When I wrote cron, it was the first time I had done any system programming on Unix. I had been working on VAX VMS since then, or before then. And so this pipe construct and the fork construct were very mystifying to me, right? And in VMS, you would call lib$spawn, and it would create this whole other thing for you, and there weren't really pipes per se. But you know, I had to learn what in fact, the purpose of writing cron in some ways was to make sure I would learn this system interface. And I got my file descriptors mixed up, right? Because on a pipe, you're supposed to write to one of the two descriptors you get back in that 2-element array, and somebody should be reading from the other one. But it turned out that in those days, the pipe call was implemented using socket pair. And it turns out that socket pair also creates an array of two descriptors, except they are bidirectional, which means that if you write to the one you should be reading from and you read from the one that you should be writing to, it still worked. But that only worked in my internal forks, right? Because cron forks 3 times as part of executing things, because it has to pay attention to your standard output and call send mail if it needs to and so forth. So that all worked fine. But it did not work on the 3rd fork, because right after that I would exec the command that you were supposed to do, and it would be reading from the descriptor that I was reading from, and then I had a deadlock, and I had hell to pay trying to figure out why is this not working? And eventually, yes, I figured out that I was using the pipe backward, and then I did some reading and found out that the pipe works just fine backward as long as the other guy uses it backward too. Really? You couldn't have found a way to maybe close it or tell socket pair some option so that it would only work if I was doing the right thing? Because I really don't want to get halfway down the track to discover that I'm on the wrong track. I want it to die soon. As soon as you do the wrong thing, I want it to die. That's, I point you again to the Equifax slide that I started with. They also mapped a page of nulls at address 0, which meant that if you looked at the null pointer, it would be the empty C string. It would start with a null character, which meant that I was able to write, and a lot of other people were able to write, a lot of broken, wrong, incorrect, hopelessly bad code that worked just fine until the day we tried to port it to something that wasn't BSD. And I just have to say again, really? Now, eventually this got fixed, and now we make sure that the 0 page is not mapped, so that if you try and access a null pointer, then you get some kind of a signal or whatever. It does what it should always have done. But this type of thinking, where you use socket pair to implement pipe, or you map a whole bunch of zeros, that was then trendy. It was, how can we make the system more resilient, more programmer friendly? And they did, with the effects that I've said. I think that demonstrated ignorance should result in an exception. And since most of us won't catch those exceptions, what I really mean is that demonstrated ignorance should lead to program death. And so in all of our design, we have to have it be that ignorance is self-demonstrating and can't be hidden. So I'm going to tell you a story about 10 megabit Ethernet, because the robustness principle, sometimes called Postel's maxim, is precisely wrong. Be liberal in what you accept, be conservative in what you send to others. You really have to be strict as hell about what you accept. And if somebody does the wrong thing, you have to make that painful. You have to make it so that they can figure out they've done the wrong thing early. So I could insert a long story here about extension headers in IPv6 and how they are going to keep fragmentation and ICMP from working, and how we're going to be stuck with 1,220 byte packets for the rest of our lives and the lives of our children and grandchildren. But instead, I'll tell you a shorter story about 10 megabit Ethernet. Certainly some of you look like you are old enough to have climbed a ladder, stuck your head up above the T-bar, looked for that yellow cable, that RG8 cable, and pull out your pocket knife and make a little hole in it, and then you take the vampire tap and you stick it on there and you put the schlunk on the back and you tighten it up real good, and then you run the cable to your Sun workstation, whatever it is, and then you've added a node to your network. That's all it was before ThinWire, before Cat5, before Cat3, before RJ48s, before switches. We had that. And that was so much better than FIDI or anything else that we'd had before that nobody complained about the ladder or the pocket knife or anything. It was cool. Anyway, I had the great fortune early in my life to have one of the 4 inventors of the Ethernet, David Boggs, as one of the listed inventors on that patent, as my mentor. And as you might expect from somebody who would design something that needed a pocket knife, he was a little bit crazy, but that was good. That was good. And so we spent a lot of time sort of cleaning up computer rooms together late at night, because neither one of us had a family and had nowhere to go. And he told a lot of stories. And one day he said, you know, the problem with Ethernet is we made it too resilient. We made it too good. And I thought, ooh, this is going to be a doozy. And it was. He told a story. He said, so what'll happen is different people with different ladders are going to be up in the T-bar at different times. And sometimes when the cable was first run, it will like go through some wall that extends above the T-bar, turn a corner, and go through the next wall. And that gives that, all you're trying to do is make sure that anywhere in the building that you might want an Ethernet tap, you could have one. And he said, so the problem is that the signal strength of the 10 megahertz signal only peaks about every 2 meters along the cable. Even later on, after we invented it, then they actually sold special cable that had black marks so that you would always know where to put your taps. But if you've only got, you know, 1.5 meters above your head, and you've got this whole computer room down there, and you don't have a hub because they haven't been invented yet, you're going to have to stick taps where they shouldn't be. There might not be any black lines, or there'll only be one, and yet you need 7 taps. And so chances are good that you're not going to go back and tell whoever told you they needed it that they can't have it. You're just going to put it on there and hope for the best. In fact, he told me a story about something he had to debug back at Xerox after this had become, I think it was 3 megabit, but nevertheless it had become production, so it was no longer a strictly research activity, where he discovered that the cable, there's a minimum bend radius, because if you take a coaxial cable and you bend it too tight, then it's no longer round. The insulator becomes an oval, and so the distance between the center conductor and the shield is no longer averaging what it's supposed to. And he said, I found a cable that had been bent beyond the minimum bend radius because the vampire taps were running into each other, and they needed to add another one, and there would only be room if they bent it so much that the other vampire taps would get out of the way. And I said, that sounds really ugly. And he said, yeah, but the problem is not there, because when you do that, it probably works, because there's enough signal strength and enough fuzz in all of this, there's enough conservatism in the design that the person who did that probably didn't suffer from it. But I guarantee you that 6 weeks later, at the other end of this cable, somebody else did exactly what they should do. They found a black mark, they cut the exact right hole, no slop, used a perfect, they've got everything totally perfect, and then plugged it in and the entire net would go down because they had used up the last bit of slack that the badness in that closet was depending on. And if we had designed Ethernet correctly, then we would have made sure that the very first time that the first person did the wrong thing, the whole thing would stop working, because then you would know what you had done wrong. And instead, we allowed people to create this amazing Byzantine mess that when it went wrong, all you could do is pull it out and start over. That's kind of what we have done here as well. So the Internet of Things is coming, and mostly it's not going to be using BSD, so it's not directly our problem. But they're going to be bringing at least 1 million new companies into the software field, and every one of these is going to be whoever won the debating trophies in school rather than whoever knows what a slide rule is or how to use it. In other words, they're going to be very arrogant, very ambitious people who are going to say, yeah, you tell me software is hard, but you're just telling me that so that I won't come in and steal some of your market share. So the hell with you, I'm going to go forward. And they're going to start hiring programmers. And they're going to need 10 million more than we have today, conservatively speaking. And they're not going to be hiring people who remember not to use getS. They're going to get fresh, undamaged programmers straight out of school, kind of like Google and Facebook do now. And these people are going to make their own mistakes. They're going to learn their own stuff. And they're going to uncover a whole bunch of unexploded munitions from the wars that we fought in. And I would like to, clean that up a little bit before they come. I can't keep them off the field. I can maybe change what field they come to. Tony Lee was famous at Cisco for being author of code that ran in Cisco routers and made the internet work. And fairly often, some ISP somewhere, could be UUNet, could be Sprint, whatever, would need a fix to something. There's something that's causing the net to not be able to grow or even causing it to fall over. And so Tony would work all night, and then he would publish an image on the FTP site, and in the email, when he would announce it, he would say, my confidence level in this image is that it booted in the lab. And we did what you just did. We all laughed. We said, it'll be fine. So mostly it was. But unfortunately, that culture became the BSD culture and is still our culture. And we're going to have to get away from it. So this idea that PDP-11 assembly language was too hard and too ugly and too unportable, and so we created C, made sense in whatever it was, 1968. Does not make as much sense now. Moore's Law has given us a lot of doublings. We have millions of what we used to have thousands of, maybe billions. We've got more RAM, we've got more cores, we've got more CPU cycles, and we have misappropriated them. We have continued to write code in unsafe languages and use unsafe libraries to create what is now the humanity's digital nervous system. It is the largest distributed system that will ever exist, is whatever the internet is then covering. And I think that's a problem. I think we should have said, thank you, Moore's Law, for doubling the number of transistors. I am not going to use that to make all my programs go twice as fast. Rather, I'm going to make them go 1.9 times as fast, and I'm going to allocate 10% of what you gave me this time towards safety, bounds checking. I have not begun to talk about heap smashing because stack smashing is all the time I had. But I do want to say that in the Go programming language, strings are not writable. If you want to make a change to a string, what you do is you take the parts you want to keep and glue it together with the part you want to change and make a new string. And because strings are not writable, there's a whole class of bugs that can't occur. You can't write getS in Golang. And I'm learning Go, and so I kind of like it, but Java works the same way. JavaScript and a lot of these interpreted languages work the same way. I'm not saying that we shouldn't be using C for anything, but I'm saying that we want to create alternatives for people who need to write applications so that when they are fresh and undamaged and they create the infrastructure that my neighbors are going to be buying and putting in their homes, that infrastructure doesn't turn into a global threat. And that's my talk, so I'm open to questions. Yes, sir. You, sir.
How familiar are you with Rust?
I've listed Rust as one of the alternatives. I'm not terribly familiar with it. Well, I guess I listed it here. I'm not terribly familiar with it, but it seemed a little bit like whataboutism. In other words, every time I would talk about Go, somebody would say, oh, well, you should check out Rust. Yeah, I don't have time to check out every possible thing, so I'm told that it is safe in this way. That's all I know about it.
What do you think should happen to POSIX?
To POSIX?
Yeah.
So I gave a...
Explosions, renovations.
So I'm going to pretend you asked me what I think will happen to POSIX, which is the question I prefer to answer. 2 days ago, I gave a keynote at the PG Open conference, that's Postgres, and it was in San Francisco, and it was well attended. I had no idea that Postgres worked inside of Microsoft Azure and that they supported it, or that it worked inside the Facebook cloud. So, clearly Postgres has got legs. But what I told them is that I had just investigated something called Ceph, C-E-P-H, that I was very intrigued by because it was one of those Linux things that somebody was doing a really good quality port of to BSD. And it's a distributed object store, so it would remind you of all the Hadoopy kind of things you've seen. But in the documentation for it, they've got these 3 pictures where they show, here's the object store, which you would use if you can speak the S3 RESTful API. And here's the, the block store that'll export storage to you as iSCSI. And then here over on the right is the POSIX interface. So if you have a legacy application that wants to store its data using files and directories and things like that, and you're going to speak to it in terms of that kind of VFSE syscall stuff, then we have that too. What that means is that it's 2 layers of emulation and that your hardware itself doesn't have any POSIX stuff on it. Your hardware itself has got a whole bunch of potentially blank disk partitions that have been given to the replication manager of the object store. And I don't know about you, but every time the thing that I have been working on is starting to be called a legacy system, I start wondering if I need to make a jump. So Microsoft has done a perfectly horrid job of supporting POSIX. Had they wanted it to make it look bad, had they wanted to drive people in droves toward the native Windows API, they could not have done a better job than to support POSIX in the form that they have. Nobody in the market thinks that they benefit from standardization of that kind. They want to lock you into their future. They want your future spending to be with them. So I think POSIX was huge for BSD. I love the level of standardization that we got by being all speaking POSIX. But I don't think that it is going to remain a force in the market. My oldest child is 26, he was born in 1991, and yeah, he can use a shell or an editor if he has to, but he's a JavaScript programmer. He uses IDEs and uses whatever the Macintosh gives him and hardly ever sees a shell or sees a directory or whatever, and he is representative of an entire generation of people who are going to write applications that do all their persistent storage through RESTful APIs. And they're going to wonder why we didn't do that back in the day. So I think POSIX is walking wounded at this point and shortly to become a zombie. Any other questions? All right, then let me say I will be here all night. I'll be at the social. I don't leave until 8 a.m. to fly back to San Francisco. And thank you again for inviting me to come here.
you.